Mic off.
Okay, we have a new lab that was posted today. It's experiment 21. It would be due next Monday, the 27th by midnight. I actually received one today early, so that'll get the 5-point bonus. And then Monday's lab was experiment 20. That'll be due along with 21 on Monday, the 27th. Oh, and the grade reports that were sent out on Monday, I forgot to mention that the calculations differ from what's on Blackboard. Like I don't have Blackboard set up to do weighting, for instance, dropping the lowest. And I don't even really trust Blackboard's calculations because too often it's happened that students see numbers that I don't see. It's like Blackboard decides to calculate some things a certain way and displays them differently for students. So I just usually input the basic info into Blackboard and then calculate all the details myself, like with the weighting and dropping however many lowest scores and so forth, adding extra credit. So if you notice a difference between the reports and Blackboards, that's why the one I sent out takes precedence over what you see in Blackboard. And the fifth and last quiz was today, and that's due by midnight. And that covered chapter 21, parts 1 and 2, half-life. And the last exam is 2 Mondays from now. That's on Monday, May 4th. And that'll cover the last couple of sections of electrochemistry in chapter 17. Those happen to be the most advanced parts of that chapter, and they showed up in the labs. Those dealt with pH and KSP. So it relates like standard reduction potentials and measurements of those to pH and KSP. And it will also include nuclear chemistry, which we're finishing up tonight, and chapter 19, coordination chemistry. Okay, so let's go on and have a look at the rest of nuclear chemistry. Okay, we talked a little bit about nuclear stability and magic numbers on Monday. Let's see, and here's the interactive periodic table at radiochemistry.org. So it has a nice colored periodic table here. And in your preceding chem class, and so far in this chem class, we've dealt specifically with chemical reactions. That is, reactions involving only electrons. The electrons are in the outer shells, and they simply just rearrange, like certain elements like to have their electrons a certain way. They like to have a certain number of them compared to other atoms. And when they come together, they just rearrange the electrons to suit themselves as a whole, like fluorine is in the column of halogens over here. And lithium's over here. Way on the other end of the periodic table, it's an alkali metal. And for example, fluorine is one electron short of a filled p shell. If it gained its 10th electron, it would put it in a pseudo configuration equivalent to neon. Neon has 10 electrons. It has a filled p shell. So if fluorine gains 1 electron, it sort of, in a way, becomes like neon. And similarly, if lithium would lose 1 electron, it would go from 3 electrons to 2, which would place it in a way like helium, which is a noble gas. And these noble gases are all on the right. They're chemically stable. They don't react. And when lithium and fluorine combine, each of them is in a sort of a stable situation like a noble gas. And they have a filled p shell that gives them 6p electrons plus these two over here, s electrons, 8 total. 8 happens to be a magic number in chemistry. 2 is also a magic number. We have 2, and then if we add the next 6 elements, that gives us 8. And if we go add in the next 8 elements, we get 16, and then keep on going. We add the next 8 plus a 10 D here. That's what, 18 and 18, 36, and keep going. And those are called magic numbers in chemistry because the noble gases have those and they're very stable. And elements tend to react in such a way so that they achieve their magic numbers. So that's how we can predict what will and won't be a stable chemical compound, is by looking at the magic numbers. And a similar thing holds for a nucleus. And we won't be going over this, but in nuclear physics, they have their own quantum mechanics, just like chemists have their own quantum mechanics. We have atomic orbitals, they have nuclear orbitals. We have shells like SPDF, and they have their shells like KLMN. And so that their outlook on things is a lot like ours, and they have their own magic numbers for the nuclei. So what does that end up looking like? Well, it's sort of beyond the scope of the class, but this graph here we looked at last time sort of summarizes to some extent. This is a graph of binding energy versus mass number. So from left to right, the elements increase in size. So iron 56 happens to be the most stable nucleus. And as we go on out, the binding energy decreases. And finally, when we get out near plutonium and the radioactive elements that are using like nuclear power, they get more and more unstable. So if we go back to here, what's going on is we're like, here's gold, here's uranium, here's plutonium, and these elements down in here in the actinides are for the most part man-made once we're after uranium. So these are man-made and they're all unstable. Some of them have a half-life of only like a few microseconds. But these are made in an accelerator, and the idea is to see what can be made by smashing nuclei together. And the thinking is that it will reach a magic number. Like if we get just a couple more spaces here, that it would produce something with a magic number that would be stable, and that would give us a new element. And who knows what kind of properties it might have. It could be really interesting, but anyway, that's the thinking of like searching for new elements, magic numbers, and all of that. So it's really strongly related to chemistry. Okay. So let's look at the last part of nuclear chemistry, which is calculating activity and dosage. And that's in the chapter 21 class notes, which is split into 3 parts. This is part 3. It's on Blackboard. Okay, this is the first page of it. It's 3 pages long. And this table here summarizes quantities in units for measuring radiation. Like up till now, what we've talked about is balancing nuclear reactions. We've talked about the particles that are emitted, such as alpha particles. We talked about what those are composed of. It's a doubly ionized helium atom. And then we have protons, neutrons, we have positrons, beta particles, we have gamma rays splitting into positrons and electrons, and so forth. So all of those come out of an unstable nucleus. And this first column here is about activity and decay rate. We've already covered decay rates as well. In fact, the quiz covers decay rates and half-lives. So this first row here is about activity and decay, and the units that we use to quantify that are called the Curie and the Becquerel, both named after famous scientists. And a Becquerel is defined as 1 decay per second. And a Curie is defined as 3.7 times 10 to the 10th decays per second. And a Curie happens to be a more practical unit to work with. So let's look at an example of calculating activity. So that the activity can be calculated from the mass of the sample and the half-life. So for example, if we have a cobalt-60 isotope, its half-life is 5.26 years, and it happens to be used in cancer therapy because it's a gamma emitter, and those gamma rays can be focused on a tumor with pretty high precision. So we want to find out the activity of a 5-gram sample of cobalt-60 and report that in Becquerels and Curies. So to do that, let's take the usual equation for a half-life, which is half-life equals natural log 2 on K, where K is the rate constant, and let's solve that for K. So we do so, rearrange that equation, and we get K equals log 2 on half-life, which is log 2 on 5.26 years, which is 0.0132, or it's 0.132 reciprocal years. And we need to calculate the decay rate in grams per year from that. And to do so, remember that K is the rate constant. If we go back to an earlier class notes, I think this is part 1, or I think it's part 2 actually. This expression is in there where we define the rate as the change in the concentration per unit time is equal to a minus K times the concentration. So this K, our K is in reciprocal years. So if we multiply that by the mass, we can use either concentration or mass. We're using mass. So we get grams per year on the right-hand side, and that is equal to the rate. And the rate, of course, depends on the mass that's present. So we're going to calculate the rate based on the total initial mass that's present, which is 5 grams. The rate actually decreases as that cobalt decays, but initially it's 5 grams times 0.132 inverse years, and we get 0.660 grams per year. Okay, now that we have the decay rate, we can convert that to decays per second, which is a Becquerel. So we take our grams per year and do some conversions from years to days, days to hours, hours to seconds, and we get in grams per second. It's 2 times 10 to the minus 8 grams per second. Now we can take that and convert to decays per second, because we know every time there is a decay, the cobalt emits a gamma ray and changes into some other element. So it disappears. So the ratio is 1 to 1. Here we have 1 atom of cobalt per decay right here as a conversion factor. So we take our 2 times 10 to the minus 8 grams per second and convert grams to moles of cobalt, then moles of cobalt to atoms of cobalt using Avogadro's number. And then over here, we get atoms per decay, which is 1 atom of cobalt per decay. And that comes out to 2 times 10 to the 14th decays per second, which is a becquerel. So this is our activity in becquerels. So it's kind of, becquerels isn't the handiest unit. It's not the most practical. So where Curie comes in, we divide that by 3.7 times 10 to the 10th, and we get 5,770 Curies. So that's the activity of the cobalt 60. It's 5,770 Curies. All right, so now let's go back up here. We've dealt with this first row, which is all about activity. The activity deals only with the source, like the cobalt in our case. The cobalt could be anywhere. It could be out in the middle of the Sahara Desert decaying where it won't bother anybody or anything. And no matter where it's at, it have the same activity, but we're also interested in the health hazards of it. And that's where the other 3 rows come in. We have ways to quantify exposure. And it turns out that most radiation, or the most risky radiation, is ionizing radiation. And we have a unit called a Roentgen to quantify that. And that's also measured in coulombs per kilogram, which is the SI unit. So this quantity is called exposure, and it gets the symbol. It has to be one of the most unhandy symbols ever chosen. It's an X for EX in exposure, so we call it X, but that's kind of confusing if you put it in an equation and you want to multiply exposure by something. So you say X times something and you have 2 X's there. But anyway, that's what it is. So anyway, we have exposure, and the unit is Roentgen, or coulombs per kilogram, and a Roentgen's equal to 2.58 times 10 to the minus 4 coulombs per kilogram. And what that measures is the charge, the ionizing charge that's imparted to whatever the radiation hits. Could be a tree, a concrete, a person, like tissue, whatever. So we have a way to quantify that now with the Roentgen. And the next row is absorbed dose. That's measured in energy absorbed per kilogram of material. And it's also known as a RAD, a radiation absorbed dose, has the acronym RAD. And it's fairly common around labs to be talking about RADs. And the SI unit is a gray, named after a scientist who studied the effects of absorbed dose on tissue. And 1 gray is equal to 100 rads, or 1 joule per kilogram. So whenever radiation actually hits something like a person, for instance, the Roentgen quantifies the charge that's absorbed, or that's the person's exposed to, and we get the coulombs per kilogram. But it doesn't really say how deep or how much energy that charge had whenever it contacted the tissue. That depends on the voltage the charge was accelerated through. Volt is a joule per coulomb. So if we take a coulomb per kilogram times the volt, which is a joule per coulomb, we get joules per kilogram, which is a gray. So that's how we go from the second row to the third row. It's like we take the second row and multiply by the voltage, get the third row in grays. And then the most pertinent quantity for us is the biologically effective dose. And that's a direct measurement of tissue damage. And the unit we use is the Roentgen equivalent man, or REM, or REM. And the REMs are what a dosimeter tag measures. Like in X-ray lab, for instance, the technicians wear a little tag on their shirt, and it measures the radiation in REM, and it's sent off to a lab every once in a while. And they report back on the number of REMs the person was exposed to. And the SI unit for REM is called a sievert. 1 sievert is equal to 100 REMs. And from the REM, we get our biologically effective dose, which has the acronym BED. Now here's a table showing the effects of short-term exposure to radiation. We have the dose here in the left-hand column in REMs. A dose anywhere between 0 and 25 REMs shows no detectable clinical effects. And I think that range is rather high, but that's what this table had. And then the range of 25 to 50 has slight temporary decrease in white blood cell count. 100 to 200 REMs shows nausea, marked decrease in white blood cell count. And I think cancer patients who get treated with radiation typically have a decrease in their white blood cell count and sometimes nausea. And then if we go to a dose of 500 REMs, that causes death in half of the exposed population within 30 days of exposure. So let's look at a calculation for biologically effective dose. And this text mentions that the typical dose for a chest X-ray is 0.05 millirems and 0.002 millirems for a dental X-ray. And it's hard to really say that these particular amounts of radiation are safe, because it depends on which part of the body we're talking about. For instance, that sort of radiation could, if it's directed towards like reproductive organs, it could be more harmful than like a hand or a foot or something like that. So because it's hard to quantify and generalize, the general idea is to keep the level of exposure as low as possible. And the rule of thumb for the general public has been to keep the limit at 500 millirems per year for whole body dosage. And it's a little higher if a person is employed in a radio lab, such as an X-ray lab. Okay, so how do we calculate the biologically effective dose? Because up here in this table, we have the definition of the biologically effective dose, or BED. and we need to relate it to the other rows. The absorbed dose tells us how much energy was absorbed per kilogram of material, but that it depends, like the actual damage depends on what sort of radiation it is. If it's ionizing, it's more damage than if it's like a beta emitter, then it'd be less damage. So we need a way to tell the different types of radiation apart. So what we do is we have this table of relative biological effectiveness called RBE for absorbed radiation. And it's a table of factors that we multiply the applied dose by. So for X-rays, beta particles, and gamma rays, the RBE is lower. It's a value of 1. If the particles are low energy protons or neutrons, then it's 2 to 5. If it's higher energy protons or neutrons, 5 to 10. The highest of all is alpha particles, because those are the most ionizing, and that'd be 10 to 20. So what we do is we take the RBE and multiply it by the absorbed dose, and that gives us our millirems. So here's an example of that. So let's suppose a person is exposed to a source of alpha emission at an energy level of 10 volts, and they absorb 0.01 Roentgen of radiation. Let's calculate their level of exposure in units of millirem. So to do this, we would first convert the exposure from Roentgen to coulombs per kilogram, and then using the voltage, which accelerates the charge and makes it more dangerous, that would give us joules per kilogram. So we take our 0.01 Roentgen, and then using the table, convert it to coulombs per kilogram. So we multiply by 2.58 times 10 to the minus 4, and that gives us units of coulombs per kilogram. And now multiply by the voltage, which is joules per coulomb, and that gives us 2.58 times 10 to the minus 5 joules per kilogram. So this tells us how much energy was absorbed per kilogram of tissue. Okay, next we convert joules per kilogram to grays and then rads. And at that point, we'll have the absorbed dose. So we take our joules per kilogram, which is the definition of a gray. So the ratio is 1 to 1. That converts directly to grays. And then we convert from grays to rads. The ratio is 100 rads per gray, and we get 2.58 times 10 to the minus 3 rads. Okay, now we can use the RBE table to calculate the millirems. So we use this equation, the bed on the left, which is millirems, equals the absorbed dose times the RBE. So we take our absorbed dose, 2.58 times 10 to the minus 3 rads, and then go to the RBE table, and we're told we have alpha emission. So here, table has alpha particles. The range is 10 to 20. So let's take an average of 15. So we multiply by 15 here, and we get 0.039 rems. And we multiply by 1,000 to convert to millirems, and we end up with 39 millirems. So that's quite a bit lower than the 500 millirems per year recommendation. And this is an example of how to calculate the millirems from a source of exposure. Yeah, you can count on seeing this sort of thing again on a test, probably the final. Maybe an X test, but it'll show up on one or the other. Okay, so let's go back here. Look at coordination chemistry. Okay, coordination chemistry is in chapter 19. And coordination chemistry is all about the D elements. Let's see if I have that. Yeah, the periodic table. Here's the D block, it's in blue. The bonding exhibited by D block elements or transition metal elements is more complex than S block or P block. And the reason for that is that there are more orbitals to work with. And so that actually the transition metals technically includes the rare earths down at the bottom, lanthanides and actinides. Those are referred to as intertransition metals because technically they are inserted here, like 57 is lanthanum, 72 is hafnium. So all the elements between 57 and 72 are actually inserted here at this spot. And the same goes for the actinides. They go after actinium at 89. So the actual periodic table, if it was laid out really accurately, would be too wide to display. So they usually split out those and put them at the bottom. So in this chapter, we're looking at how these elements bond and why they bond the way they do. So ultimately, the reason they have their bonding properties is because of where their electrons can go. And these are the d atomic orbitals is calculated for a hydrogen atom. And that's where we get our sp, d, f, g, and so forth orbitals. It's from quantum calculations for an H atom. And these are idealized. The actual orbitals can look different from this. They can be combinations of what's shown. It just depends on where the electrons need to go for it to be stable. But one thing we can count on is that the orbitals will be symmetric. And what we end up with a lot of times is 4 ligands or attaching atoms in one plane, separated by 90 degrees, and we have an additional one above here and one below. And if we connected all the red attached atoms here, like drew lines from one to the other, we would have a square base bipyramid or an octahedron. So these metals often form octahedral complexes. Okay, so let's look at the chapter 19 class notes, which are here. And on the first page, there's a list of quite a few definitions which pop up all the time, like a ligand, for instance, is also known as a complexing agent. That is an ion or a neutral molecule attached to a central metal atom. And a complex ion or a complex is a metal cation that's surrounded by 2 or more ligands. The octahedral complex I just mentioned is an example of a complex. Here are a few examples. We have a gold attached to 2 cyanides. with an overall charge of -1, and the brackets indicate that we're dealing with a complex ion. And another example is iron attached to 6 water molecules with an overall charge of +3, or cobalt attached to 3 oxalates with an overall charge of -3. So all of those are examples of complex ions. And the term coordinate refers to the process where ligands organize and form a symmetrical molecule or complex ion. And a coordination compound is another word for a complex ion. The coordination number is the total number of ligands attached to the metal. And the donor atom is the atom of the ligand that's bound directly to the metal. Like up here in these chemical formulas, we could have, for instance, iron, where it's attached to 6 waters. The particular donor atom it's attached to is probably the oxygen. So in each water, the donor atom would be oxygen, and collectively that makes up the coordination compound or the complex ion. And in this case, the water would be capable of occupying one donor site. Like in FeH2O6, there are 6 sites forming the octahedron, 4 in the same, like in the XY plane, and 1 above in the Z plane, 1 below. That makes 6 total. And each water is capable of occupying one of those sites. But some of the larger molecules are capable of occupying more than one site. If they can only occupy one site, they're known as monodentate. And the mono meaning one, and dentate refers to teeth, like a dentist. So dentate means it has, or monodentate means it has a single tooth to latch onto the iron or the central atom. If it were bidentate, it would have 2 teeth, and we could have polydentate. Actually, this is a typo. This should say polydentate, not mono. So a polydentate ligand possesses 2 or more donor atoms that are able to occupy 2 or more coordination sites. And sometimes these compounds form ring structures, and those are referred to as chelates. And here's a list of common ligands found in complex ion. We have lots of ligands for monodentate. Water is a prime example, or ammonia, cyanide, hydroxide, fluoride, chloride, bromide, iodide. Those are all the halogens. And then we could also have nitrite, thiocyanate, or thiosulfate, and there are others. And they can be neutral, like water or ammonia. In those cases, water and ammonia have a lone pair of electrons to donate. And then in the case of the ions, there are additional electrons forming the lone pair that they're able to use to bond to the metal. An example of a bidentate ligand would be oxalate, and also ethylene diamine, which is, for simplicity, abbreviated EN, plus a couple of others. And then we have polydentate ligands, and one that has 3 is a diethylene triamine, and the most well-known one is called EDTA, for ethylene diamine tetraacetate. It has 6 coordinating atoms. It's used as a food preservative, among other things. So here's examples of the chemical structures of bidentate ligands. Here's oxalate on the left and ethylene diamine on the right. And the next drawing shows how they attach to a metal. In the case of oxalate, the two oxygens can come together from opposite sides and fill two coordination sites on the metal. And in the case of ethylene diamine, it's similar with the amine groups, the NH2, with their lone pairs attaching to the metal from opposite sides. And it looks a little more complicated for polydentate ligand, especially EDTA. Here's the structure of EDTA. Here's at the four corners here. If we go clockwise here, 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 and here, those are the four acetates. It says tetraacetate, so there are four acetates, and then the ethylene diamine is in the middle. Here's the ethylene part, and here's one of the diamines, and the second diamine's over here. Or I mean, it has two amines. It's ethylene, there's the first amine, and over here is the second amine. And each amine is attached to two acetates. So whenever this compound loses its hydrogens, that gives it three unshared pairs on the oxygens. And when this is put into a solution with the metal, it's easy for this molecule to curl around a metal and form a structure around it, which looks like this. Here, the brown sphere in the center is the metal. And the rest of it is the EDTA. And these drawings where everything looks nice and neat and linear is mainly for our own understanding of things. If you've ever made a model from a model kit of a long molecule, you'll notice that it's when you add more and more carbons in a chain, it naturally curls up. If you make a model of a long bunch of carbons, all at their tetrahedral angles, and toss it around, you'll see it'll curl up into a helix. So normally these molecules are like helices. So it's easy for them to wrap around a metal like that. So now we're going to first figure out how to name these. We have a set of nomenclature rules for metal complexes. For example, when we write formulas for metal complexes, the symbol for the metal ion is always given first, followed by the ligands. So the metal, which is positive, goes first, followed by the ligands, which are usually negative. And one way of remembering that is the usual rule of thumb for management, like on the job where a manager is ideally supposed to mention something positive first before bringing up something negative. Like if they have a gripe with a job somebody does, they first bring up a positive thing or two and then ask about the negative thing. So that way the employee doesn't think that that all he has is negative opinions. So anyway, the metal's positive, that goes first, and ligands are negative, they go last. And when more than one kind of ligand is present, the anionic ligands are written first in alphabetical order, followed by the neutral ligands, also in alphabetical order. And then we keep track of the charge. The charge on the complex is the algebraic sum of the charge on the metal and all the ligands. And then we put it all in square brackets and with the charge as a superscript. And unless it's neutral, then we don't need the brackets. So here's an example. we have an iron 3 ion forming a complex with 6 cyanide ions. What is the net charge on this ion, and what is its formula? So to find this out, we would need to take our 6 cyanides. We know from the rules of nomenclature that we've already done, cyanide carries a -1 charge. And if we have 6 of those, that's a -6 altogether. Iron 3 has a +3 charge. So if we have +3 -6, that gives us -3. So the net charge on this ion has to be -3. So we write our brackets as shown here. And, oops, zooming in. So we put everything in brackets here. And then inside we put our iron first. That's the positive part goes first, followed by the negative, the cyanide, and we have 6 of those. So we get FeCN6 inside the brackets with an overall charge of -3. Okay, another example is silver forming a complex with 2 ammonia molecules. And what is the formula of this ion? And can it exist with a sodium or a chloride? And we're supposed to write the formula of the possible salt. So here we have 2 ammonia molecules. Ammonia is NH3, which is neutral. So we have silver attached to 2 ammonias here inside brackets. And silver is +1. So we have a +1 on the outside. Now, the second part of this, it asks if it will combine with sodium or chloride. So because it's a positively charged ion, it should combine with the chloride, which is negative. So the formula of the salt would be the silver ammonium or silver ammonia complex in brackets followed by chlorine. Another example is a complex containing chromium, 2 ammonia ligands and 4 nitrite ligands. So the rule is the positive first, chromium, followed by ammonia, NH3, it's a neutral. There are 2 of those and then 4 nitrites. So if we have 4 nitrites, that's 4 -1 charges, totaling -4. And if that's in combination with chromium +3, that gives us an overall charge of -1, which is what's superscripted outside the brackets. So that would be the formula for this compound. And then here, the last one is cobalt 3+ with 2 chlorides and 2 ethylene diamine ligands. That's the one that gets abbreviated EN. And EN's neutral. So we have a cobalt 3+ written first, followed by the 2 chlorides and then 2 neutral ethylene diamines. So the cobalt is a +3 and the 2 chlorides make a -2. Just take the 3 minus the 2 and we get a +1, which goes on the outside of the brackets. So those are 4 examples showing how to write the formulas. Now, writing names is actually quite a bit more involved. And there is a set of rules for this. and these rules are in Jesperson. There's a somewhat shorter version here in these notes. But some of it's similar to what we've just done for the formulas. For instance, the cationic species is named before the anions. And that's similar to how we've been naming things all along, such as sodium chloride. So the metal goes first. And what's new here is the names of the anionic ligands always end in the suffix dash or the suffix O. For instance, if we have a chloride ligand, it's an anion, so we call it chloro. If it's bromide, call it bromo. Cyanide is cyano. Oxide is oxo. And ligands whose names end in ite or ate become ito and ato. So carbonate becomes carbonato. Sounds kind of Italian. And thiosulfate becomes thiosulfato. Thiocyanate is thiocinato. And by the way, that's when bonded through the sulfur. If it's bonded through the nitrogen, it's called isothiocyanato. Oxalates, oxalato, nitrite, nitrito, or nitro, depending on which atom it's bonded with. And a neutral ligand is given the same name as a neutral molecule. And it'd take a while to just go read through all this. It's probably easier just to look at some examples. Some of the rules are kind of like what you're already familiar with, like writing stock symbols with Roman numerals. So there are some examples here in the class notes you can try for practice, and then the answers are given on the next page. So that way you can practice without peeking. Just don't turn the page over and look until you're really scratching your head, then peek. Okay, so let's go here to the PowerPoint and look at some nomenclature examples. I'm going to stop for a second just to see who all we have. Okay, so looks like we have Maddie, Brennan, Elizabeth, and Diana. So let's try working through these together. I'll do the first one. Okay, let's write the IUPAC name for this complex. So let's first look at the charges. First, the ligand is cyanide. We have 4 of them, each one bearing a -1 charge. So the total charge associated with the ligands here is -4. And the overall charge is -2. So now we can figure out what the charge on the nickel is. So that the charge on the nickel, we call it X. If we add the charge of the cyanide, which happens to be -4, we get X -4. And that sum is equal to the overall charge, which is -2. Solving that yields X is +2. Which is a charge on the nickel. So that gives us the stock symbol for nickel. It's nickel 2, the Roman numerals. And according to the rules, we call that nickelate because the metal is attached to an anion instead of a neutral. So it gets the ATE on the end. So The nickel will be called nickelate. And then we go back to the ligands. We have 4 cyanides. The Latin for 4 is tetra. And this is an anion, so it gets the O suffix. So instead of cyanide, we call it cyano. And then we have an overall charge of -2, which is non-zero, so we append the word ion to it. If it were neutral, we wouldn't need to do that. So if we put this all together, the name is tetracyanonickelate 2 ion. So that the tetra, cyano is for the 4 cyanides here. And then the nickelate refers to the nickel. And then the 2 is a charge on the nickel. And the phrase ion at the end tells us that there's an overall charge, that it's not a neutral.
Mic off.
Okay, so let's try another one. Okay, this
Mic
one's
on.
cobalt with 4 attached ammonias and 2 chlorides with an overall charge of +1. Okay, Maddie, what would we do first here?
Would we like pick the charges?
Okay. Okay, which one?
For the ammonia?
Okay. Okay, and what's the charge on each ammonia?
+4.
Well, actually, each one happens to be neutral, but there are 4 of them.
Okay, but there's 4 of them. Okay, so they're all right.
Okay. All right. So yeah, that was the right starting point. Okay, Diana, what would we do next?
We find the overall charge.
Okay, and what's that?
It's just +1, right? It's just positive.
Okay, right. Okay, and what about the chlorides? What would those be?
2 +2.
Well, chlorine's right next to the noble gases. It needs to gain an electron, so it's going to be negative. Yeah. Right. Yeah. Okay. Yeah, right. If we take cobalt and call it its charge X and add the charges of the rest, we get X +0 for the 4 ammonias plus a -2 for the 2 chlorines, and that sum equals the overall charge of +1. Yeah, so that gives us X equals +3. Okay, so Elizabeth, what does this tell us about the name of the metal?
I have no idea.
Well, what's its charge?
Positive? 1?
No, isn't it neutral? Is that?
It's right here.
The charge of... I'm confused.
Yeah, it tells us that it's named to be cobalt-3 in Roman numerals. All right, now a little tougher question is what will its name be in this complex?
Ooh.
Well, that could be. How about the metal though? Yeah, but let's take it a step at a time. What would the metal be all by itself? Yeah, right. Yeah, cobalt-8. Okay, here's a kind of a tough question. What about the name of the ammonia? Hey, Maddie, what would that be?
Isn't it like tetraamine? Something
Right,
like that?
and how's amine spelled?
Oh jeez.
That's the tricky part.
I think it's like AMMINE.
That's right. Yeah, we use 2 M's. Normally it'd have 1. Yeah, so we have 4
Well,
of
doesn't
those.
ammonia have 2 M?
No. Oh, yeah, ammonia does, but amine doesn't. Yeah, so if we have an ammonia neutral, it's given the word amine, A-M-M-I-N-E. Amine is usually an NH2 attached to something else, like a carbon backbone. But for naming these, we call ammonia amine with 2 M's. Now, what about the chlorine? About Diana, how would that be named?
I'm not really sure.
So we have 2 of them. What would the prefix be? Before it was tetra.
Di.
Right. Yeah, so we have di because there are 2 of them. Remember the rule, if something is an anion, the IDE is replaced with an O.
So like dichloro.
Right. Yeah. Yeah. So we get chloro. And it happens to be inside the brackets. So it's actually part of the complex. So we call it chloro. If the chlorine were outside the brackets, that would be chloride. It would keep its original name. Okay, now we have an overall charge of +1. So if we have to end the name with ion, now the trick is putting all this together in the name. Hey, Brennan, what did you say earlier? Okay, let's see. It's pretty close. The tetramine, the dichloro, are in opposite order, and cobaltate 3 ion. So the rest was fine. Well, well, actually, I think the rule said that the anion is supposed to go first, and I think maybe the rules need a little rewording or something. But this is a accepted name for it, and they're in alphabetical order. That we have amine starts with an A, and then the chloro, which is a C. So we have amine first, and then chloro for that reason, followed by the metal cobaltate. So in the formula, the metal goes first, but in the name, it doesn't. It goes last. Okay, let's try another. How about this one? We have a sodium, chromium, and some other stuff in there. Okay. Okay, Elizabeth, what would we do to start this?
Find the charges of them.
Okay, which one?
Um, do you start inside the bracket?
Oh, we can. That's fine.
Yeah, I don't know.
Well, how about the NO2? Yes, first, what would the name
Is
of
it
that, what would the charge of that ion be?
1 minus?
Right.
And
Yeah,
there's 6, so it'd be -6.
Okay. Oops. Okay, so let's do sodium next. Okay, Maddie, what's the contribution of the sodium?
Isn't it just like a +1 charge?
Right. And what's the total? The total of sodiums.
3.
Okay. All right, so we have +3 contributed by the 3 sodiums. And we have a -6 from the 6 NO2s. Okay, Diana, what would the chromium be?
Isn't it just +1?
Well, it might be. We'd have to figure it out. Right, yeah. So yeah, let's do the algebra. Let's assign X for the charge of chromium. Yeah, so the sodiums add up to +3. Chromium is X. And the 6 NO2s are -6. All that adds to 0, which means that X must be +3. Okay, so what would the name of this metal be? And what's its charge? Or what's its symbol? Its stock symbol. How about Elizabeth?
I'm actually really lost on how to do like all of this.
Wait,
Okay.
what are we finding the name of? Like the inside of the bracket or the whole thing?
Just the chromium.
Just the chromium? Oh.
Okay, right. And what would its name be? Or how would its name be written? Yeah, chromate. Yes, chromate. By the way, I'm only seeing 4 people, like 4 of you online. If someone else is out there and they're not being called, just let me know. Okay, so the next part, oops. Okay, and how about the Na? How would we name it? It could be tri,
Yeah, I thought you just put sodium.
but normally we don't need to say tri because sodium's always +1. Like like if we had sodium sulfate, we wouldn't need to say disodium sulfate because we'd know by hearing it that sodium. Right. Yeah, so we, in this case, we don't need the tri, we just say sodium all by itself. Okay, now the little tougher one is naming the NO2.
Is it hexanitro?
It might be, I think it sounds good. Hexa, it's an Italian version of that, nitrito or nitrito. Yeah, so you're very close. All right, and then the overall charge of 0 tells us that we're not dealing with an ion, so we don't have to append the word ion to it. So now we're all ready to put this all together into a name. Okay, Brennan, you want to try this one? Yeah. Yeah, sodium split off since it's outside the brackets. Yeah, sodium hexanitrito chromate 3. Oh, here's another one. This one has silver in it, silver and ammonia. Okay, let's start with the ammonia. Okay, Diana, what would the charge be for the NH3?
+2. +2.
Well, there are 2 of them, but NH3 happens to be a neutral. Yeah, so it'd be, yeah, there's no charge on NH3. Yeah, so overall, it doesn't contribute. Now the silver, well, the overall charge is +1. Okay, so Diana, what would the silver be?
+1.
Right, yeah, it's +1. Okay, so Elizabeth, how would we name the metal for this? How about Maddie?
Isn't silver one of the ones where we just call it silver? Or like, don't we pick the like Latin name of it?
Yeah, either way is okay.
Let's do silver.
Okay, yeah, that's simpler. Okay, so it's silver 1. Well, we actually, I think
Is that the?
yeah, we could just, yeah, we could say silver, but anyway, I wrote this using argentate. So let's just go with argentate since it happens to be in the PowerPoint. But you're right, yeah, silver. The word silver could have been used instead. All right, now how about NH3 naming it? Hey, Diana, what would that be?
It's like Wasn't it like before when it was like amine?
Yeah, you're right. Yes, correct. Yeah, and how about the total number of ammonias? How do we name that?
Um, so there's 2, so diamine.
Right. Yeah. Yeah, there's 2. So we use di. We have the ammonia neutral, so we use amine with 2 M's. Okay. So looks like we have an overall charge of 1, so which isn't 0, so we need the word ion at the end. Hey, Maddie, do you want to take a stab at naming this?
Yeah, would it be diamine argentate 1 ion?
It sounds good. Yep, that's right. Diamine argentate 1 ion. All one word, not even a space between the parentheses and the E. Yeah, we could have named that with silver as well. So either of those names would be okay. Right. Yeah, the prefixes only go on the ligands. Okay, let's try another. How about this one? We have cobalt, then En, and chlorine. Okay, let's start with the charge. Okay, Brennan, how about the En? How do we name that? Right. Okay, that's ethylene diamine. Okay. And then, okay, the 3 chlorines. Okay, Maddie, how would we account for the charge of the 3 chlorines?
It would be +3.
Close. It needs a little adjustment.
I'm not sure.
Well, chlorine is, is it negative?
-3.
Yeah, it's -3.
Oh, okay.
Okay. And okay, Brennan, what would the charge on the cobalt be? Right. Okay, so now then, how do we name the cobalt? Hey, Diana, what would that be?
Cobaltate.
Yeah, so far so good. How about the symbol?
3.
Yeah. Oh, whoops. I forgot it's not a cobalt date because it's not attached to an anion. It's attached only to a neutral, so we keep cobalt as is. We only add ATE onto it if it's attached to a ligand that's negative. Yeah, so yeah, it keeps the name cobalt. All right, how about naming the EN?
Is this one of the ones where you put the S? Oh, never mind. I saw it.
Yeah, you were right. Yeah, it's a try, but yeah, we changed that to tris and put ethylene diamine in parentheses. And the reason for that is if we didn't use parentheses and we didn't use tris, that is, if we just put a tri there in front of ethylene diamine, it'd be confusing because we wouldn't know if it meant that we have 3 ethylenes attached to 2 amines. But what we really mean is there are 3 ethylene diamine groups. So with tris, it makes it more obvious, and also with the parentheses. Now, how about the 3 chlorines? How do we name that? How about Maddie?
Is it chloride?
Right, yeah, because it's outside the brackets. If it were inside, we'd say chloro, but it's outside, so we keep it as chloride. Okay, and then the overall charge was 0, so we don't need the word ion. Okay, who wants to take a try at putting all this together?
Is it trisethylene diamine cobalt 3 chloride?
Sounds good to me. Yep, that's it. That's right. Yes. Oops, that's the last one. But Brennan, regarding your question, that relates back in the periodic table where elements in certain columns always had the same charge. Like one of the columns was the halogens, always -1. And then oxygen and sulfur, selenium, tellurium, always -2. Nitrogen's -3. And aluminum's always +3. And all of the alkaline earth metals are +2, and all of these are +1. So in all of those columns, we don't use prefixes like di, tri, tetra, and so forth. Okay. Well, that's about all I had today. Are there any questions?
I'm good.
Okay. All right, let me shut this recorder off.